All right. So, basically is all I had to say about the second order biquad, right. Now, let us see the issues that crop up when you cascade a bunch of biquads. I mean, after all, we are interested in realizing a high order transfer function, right. And therefore, as we discussed, when we try to realize a high order transfer function, what we are going to do is split up the transfer function into products of first and second order sections, and then just put them in cascade, all right. And it's easiest to work with an example. So, let us say we are interested in building a third order right. A third order butter. All right. And how does the transfer function look like? H of s is nothing but 1 over 1 plus s over omega naught times, it turns out, as we discussed in class the other day, it is nothing but s over omega naught plus s square by omega naught square. This is a third order Butterworth filter with a bandwidth 3 dB bandwidth given by omega naught. Now, we say, okay, let us try and figure out how to realize this. Well, we will say we will realize this as one section, and this obviously is the other section. The first order section, well, we already know what to do. Okay. So, we choose RC is equal to 1 over omega naught Vi, and then we follow it up with our good friend the second order section, which is and what is Q for the second order stage? It's simply 1. So, quite conveniently choosing all resistors to be the same and all capacitors to be the same gives you a third order Butterworth filter, right, and the bandwidth being 1 over omega, the bandwidth being 1 over RC, which is omega. So, this is H of s. Now, I would like to draw your attention to a couple of points. So, what comment can we make about the frequency response from Vi to, let us call this V1? At omega naught, what is the DC gain? magnitude, I am only interested in the magnitude. So, the DC gain is 1, at omega naught it will be something like 1 by root 2, which is like 0.7, right, and it looks like this, right. I mean, this is probably not really accurate picture, but you get the idea. And what is the response at the output? What is the response at the output? Well, the overall response is much flatter and sharper, and probably does something like this. Okay, so that is VO by VI, and this is V1 by Vi. But what comment can we make about V2 here? It is band pass, that's correct, and it's band pass from here to here, correct? Okay. But what comment can you make about the comment? I am interested in the transfer function from here to Vi to V2. Okay, what comment can we make about the transfer function from V1 to VO to V2? It's band pass. So, that is nothing but S by omega naught. Remember, let us recall what the band pass transfer function was. It is simply nothing but S by omega naught divided by the denominator polynomial. So, it is simply S by omega naught divided by S square by omega naught square plus S by omega naught plus 1. So, what comment can you make about the peak gain or the gain at omega naught? Okay, at very low frequency, how will the band pass response look like? At DC it is 0, but at low frequency, how will it go from 0? S square terms will become negligible. So, it basically does something like this. At omega naught the gain is 1, right. So, it does something like this, and then it goes to 0 at omega naught is equal to equal to infinity. This is nothing but V2 over V1, that is the band pass transfer function. But what I am interested in is not V2 over V1, but V2 over Vi. So, what comment do you think you can make? So, what do we do to get the magnitude response at of V2 over Vi? We simply multiply this curve with this curve, and therefore, you will expect to see something like this, where the peak will now only be actually the peak will not occur at omega naught, it will shift slightly to the left, but I mean that shift will be so small that at this point does not matter. Because intuitively you are multiplying a curve which is doing this with a curve which is doing this. So, the maximum of the peak will shift to the left. Alright. So, what I want to point out is the following, right. So, the peak, so as you sweep frequency, input frequency, what do you notice here? The peak swings at the outputs of each op amp are different, alright. So, and why are we interested in the peak swings? Remember that the op amp being ideal and the virtual ground being a short and all that is only valid under the assumption that the op amp is in its within quotes high gain region of operation, right, and that's only valid as long as the outputs of the op amp don't get too close to the positive and the negative supply rails. All right. So something that we have to contend with is that if you go on increasing the input amplitude, you will eventually reach a point where the op amp saturates, in which case the virtual ground is no longer virtual ground, and there is no longer a transfer function. The system has become nonlinear, right? So what we want to do therefore is we would like to avoid op amp saturation, right? Okay, and we'd like to avoid op amp saturation for an input signal which is as large as possible, right? And the reason behind that is the following. Let us say that because of some weird choice of resistor values here, right, the peak gain of one of these op amps was much higher than the peak gain of others, right? And to illustrate the point, what I am deliberately going to do is I am going to gain this node up by a factor k, let us say a factor 10. Okay, if I just make that resistor 10 times larger, what comment can we make about the transfer function of the biquad? Will it change or will it remain the same? It will? The question is, what will be the transfer function of this biquad? When I go and change that resistor by, let me just make this round number, let me make it a nice number, let me make it 9. Okay, hopefully this gives you a clue, right? What comment can we make about the transfer function of this biquad now? Will it remain the same or will it change? Or the omega naught and q of the biquad, will it change or will it remain the same? Okay, before I put that 9, what is the transfer function from here to here? One upon SCR. What is the what is the transfer function? 9 upon SCR. So it's like changing, it is equivalent to taking that original integrator and changing one of the capacitors by reducing the capacitor by a factor of 9, right? Okay, all right. So now, will that mean that the closed loop, the poles will move or will they remain in the same place? I am not interested in finding out where the poles are. First, tell me whether you think the biquads omega naught and q will change or they will remain the same. They will change, correct? In fact, if you go and do the math, it turns out that the unity gain frequency, which was 1 over RC earlier, now becomes 3 over RC because this is increased by 9 times. But that's not the point. Right? The key point is to understand that by changing one of those resistors there, for instance, the poles of the biquad and the quality factor have both changed. All right. Now the question is, what do I do to bring it back to omega naught? What do you think I could do? Of course, one thing you would say would be to, hey, don't change the 9 in the first place, right? But let's say I want to do it anyway. What could you do to bring the omega naught and the q back to what they were originally? Pardon? What is the simplest thing? If you had to just change one element, what do you think you could do? Okay, one thing you could do is increase the capacitance by a factor 9, right? Alternatively, there are many ways of doing this. An alternative way would be to simply increase this resistor also by a factor of 9, right? And what is the intuition behind that observation? So this voltage has gone up by a factor of 9, right? But if you want the transfer function here to remain the same, this current should be divided by 9, that's all, correct? So in other words, multiplying this by 9 and dividing this resistor by 9 will result in the same transfer function for the biquad, correct? And therefore, the same transfer function from the input of the filter to the output of the filter, right? Now, the question is what has, what else has happened because the resistor is increased by a factor of 9, right? The input output transfer function obviously is the same, correct? What comment can we make about the transfer function from Vi to V1? It remains the same. What comment can you make about the transfer function from V1, Vi to V2? Is it the same? Why?
Because of what's coming to the Pavan, it is not changing.
Correct, right? The input output transfer function we know is not changed. So, well, as far as V2 is concerned, I mean the same current comes to that branch. So, the transfer function at V2 has also not changed, right? So, this is nothing but V2 over Vi. What comment can we make about V3? What was it earlier? If that 9 wasn't there, what was the V3 by Vi earlier? Same as V2 by Vi. But now what has happened? Oh, well, oops, right? So, this has gone up by a factor. Actually, not a particularly good artist, but right, I think you know what I mean, right? So, let me kind of draw a cartoon. So, in other words, if this was the original transfer function of V1 was something like this, V2 was something like V3 was something like that, and V2 was the same thing. Now, what happens? Well, we have one, this is say 9, okay, and what is this transfer function? This is nothing but V3 over Vi, and just in case, all right. Okay, so now the question is, hey, is this good or is this bad, or it doesn't matter, or what? Pardon? So, let me call this A1, AMP2, opamp3 and opamp4. So, if you did this, A3 will go into saturation. What is the question I would like to ask therefore is, let us assume that the op-amp saturates if its output voltages go higher than plus Vsat or lower than minus Vsat. And this Vsat is a function of the power supply. You've already taken analog design classes. You know that at some point in time when the voltage at the output goes very large, then some device goes either into the triode region or gets cut off or one of those things, and therefore there is some limit there which depends on the supply voltage. We assume those limits to be plus minus Vsat. So, the question I would like to put to you is, what is the largest input amplitude of a sinusoid I can use, right, before any one of the op amps gets saturated, right? And why do we say any one of the op amps gets saturated? I mean, the other three guys are working quite nicely. Why should we? Is it a problem if just one gets saturated? Well, I mean, once one of the op amps gets saturated, right, the notion of transfer function doesn't exist anymore because the system has become nonlinear, right? So, what is the maximum input amplitude that you can put in before any one of the op amps gets saturated? It is simply Vsat by 9. Does it make sense? All right. in this particular example, we see that even when the input is a sinusoid at omega naught, for instance, and has a voltage, has an amplitude which is Vsat by 9, then A3 will just reach the edge of its swing limits and therefore saturate, and beyond that A3 is within quotes gone FUD, alright. And therefore, the filter is basically now no longer a linear system, it's non-linear, and all sorts of weird things happen, and we are not interested in that, alright. So, what do you think is the design flaw therefore with this choice? I mean, evidently the transfer function as far as the input output is concerned is still maintained, that is not changed. But it just so turns out that this particular choice of resistor and capacitor values have led to a scenario where one of the op amps, namely A3, prematurely limits the maximum input swing that you can put in to the filter, right. And let me reiterate, in an ideal network theory world where op amps are, can take infinite output swing, there is no difference as far as the transfer function is concerned, whether you use 9R there or you use 1R, right. But in practice, we know that op amps must operate of a limited supply, which means that they have limited swings, which therefore means that if you make the input larger and larger, at some point some op amp will get into the saturation region, beyond which the system is no longer what you want it to be, right. And this particular choice of resistors and or capacitors, right, is it a good choice, or can we comment on whether it's a good choice or a bad choice? It's a bad choice because while A1, A2 and A4, right, have maximum gains which are 1 or smaller, right, you have something which has a maximum gain which is several times larger than 1, right, and therefore you basically are in a situation where A3 prematurely limits the maximum amount of input signal you can put in before the system becomes null, right. So, to summarize, while there are an infinite number of choices of choosing the resistors and capacitors to achieve the same transfer function, right, many of those choices will be poor in the sense that one or the other of the op amps will prematurely limit the maximum input signal swing that you can put in. Does it make sense? Alright, okay. So, what is the moral of the story? So, how do we fix this problem? What should we do therefore? What would you do? I mean, let's say somebody came and told you that, oh well, here is a third order Butterworth filter, I have done the math, the transfer function is what I want, alright, okay. And oops, it seems like even when I put in Vsat by 9, the filter is going berserk, right. Help me fix the problem, right. What would you do? How would you go about fixing the problem? So, what you would do therefore is plot the frequency response from the input to the output of every op amp, right, and you will get therefore frequency responses which which in general can look, this could be V1, let us say, this could be V2, again this need not pertain to this filter, could be something else, this could be 1, this is 1, let us say, and then you have something else which is V3, right. This is all as a function of frequency, alright. If you have a high order filter, at the output of every op amp, you will be able to plot a frequency response from the input to the output of every op amp, correct. And in general, there is no reason that the peak gains of all the op amps are, there is no reason for the peak gains to be identical, right, okay. So, one op amp's peak gain is bound to be higher than all the others, right? After all, it's a maximum of n numbers, right? Okay. So what comment, let us say, A2 has the highest peak gain when you plot the frequency response curves as shown in this picture. What comment, therefore, what conclusion can you draw? If A2 has a peak gain and that gain turns out to be, I don't know, 22, what comment can we make? What comment can we make? No, that's the how do we fix the problem, but what do we do with how do we? So the conclusion is that A2 limits the maximum input you can put in, and it limits it to V sat by 22, right? And ideally, what is the maximum input you would like? V sat, correct? So what would you do? Therefore, how would we fix the problem? We'd like to. So therefore, if you look at I'm going to illustrate it when we have a capacitor here, right. So let's say this is the kth op amp, all right, and let us say the peak gain at Vk when we plot and then this goes on and this goes on, all right, and let us say we have a peak gain Vk by Vi, and that peak gain is say M, all right, and what comment can we make about what should we do now? We'd like to reduce the peak gain of the frequency response from Vi to Vk, but without changing the transfer function. That's the key point, right? So if you want, there are many ways of doing this. A simple foolproof way that works is the following. Remember that the voltage Vk is basically this current times the impedance, correct? So if you want to reduce the voltage by a factor of M, and what do you want to reduce it to? The peak gain is M. What do you want to make the peak gain? You want to make the peak gain 1, correct? All right. So to reduce the peak gain by a factor of M, what should you do? The current that's flowing in, let us say you don't want to mess with, the voltage is current times the impedance that's across the op amp. So what would you do? Reduce the impedance. So what should I do to this capacitor? I should reduce the impedance, so I should basically increase the capacitance by a factor of n, all right. But if I just did this and did nothing else, what would happen to the transfer function? The transfer function will change, because the transfer function is what it should be only if the peak gain here is M times Vk. Now it is M times smaller, and therefore the current flowing through Rk plus 1, right, has also become M times smaller, all right. So if you want to bring the transfer function back to what it was earlier, what do you think you should do? We should have the same current that was flowing in that resistor, okay, as we had before. So what should we do? You reduce this resistance by a factor of, all right. So this way, as a result of this operation, what comment can we make about the frequency response now? if I want to draw the frequency response on the same picture, what will happen? What will happen to the shape? The shape remains exactly the same. It's only the peak gain that goes down by a factor of m. So what was m earlier is now 1. Does it make sense? Right? Okay. So we figured out a way of making the peak gain at the output of the op amp of one particular op amp 1. And what should I do now? Okay, so we have to do this procedure for all the op amps. There is no need to do it, one op amp at a time, right? Okay, it is very straightforward to. All that you need to do is plot these frequency responses. That's that's one measurement, right? You know the peak gains, right? And you can do this in all this in one shot. For example, again, I'm going to take a section of a larger section. And just for argument's sake, I'm going to make this a resistor. Let's call this RA, CA, RB, RC. This is VK, this is VK plus 1. Let's say, for argument's sake, that the peak here of the frequency response from Vi to Vk, let's say the peak gain was G1 and the peak gain was G2. We want the peak gains at both these outputs to become 1. So, rather than do it one op amp at a time, if you want to do it in one shot, what do you recommend that we do? What do we do? So, we'd like to push this gain down by a factor of G1. So, what would I do? Oh, well, you just reduce this by, you increase this by G1 and reduce that by G1. Okay. I need to reduce the peak gain of this by okay, let's say this is going somewhere else, this is going somewhere else. That happens. That scenario is very clear. For example, look at this guy, for example. We see that its output, not only goes to, it is driving two resistors, right? One is, of course, fed back on itself. So if there are multiple resistors connecting at the output of an op amp, so let's call this RD and RE. What should I do now? What would I do? RC must become? The peak gain at Vk plus 1 is G2. I have to reduce its gain by a factor of what?
By factor of G2, but we have already made RB to RB by G1. So now the gain becomes RC divided by
No. See, that's remember, multiplying this by G1 and dividing this by G1 has not changed the current that's flowing into through that resistor, correct? All that it has changed is the peak gain there, right? So what do we need to do? We just need to change RC to RC by G2, right? That will push the peak gain at Vk plus 1 down to 1. And then what do we need to do? All the other resistors that are sensing this voltage should know that the voltage has changed. I mean, you know, the current through them should remain as it was before, right? So what comment can we make about RD and RE? Both of them should be divided by G2. Right? Okay. So in general, a filter basically will potentially have this is the output of some op amp, this goes to some virtual ground or the other, right? If this is C, this is R1, R2, R3, and if you want to if you want to scale the peak by a factor of m, you basically multiply this by a factor of m, alright. That will pull the peak down by a factor of m, and then you divide all these resistors by a factor of, right. You do this at every op amp, and all this can be done in one shot, okay. The end result will therefore be, this process is what is called dynamic range scaling, alright. Okay. And what is the end result? After dynamic range scaling, what happens? What comment can we make about the peak gains at the outputs of every op amp? They are all 1, right. So, therefore, no single op amp prematurely limits the peak swing that you can put in to the filter, okay. So, all the op amps kind of hit saturation at Vset, right, and you basically all the the input that you can put in is the sinusoidal input that you can put in is, at least in principle, Vsat. This assumes that the op amp is all fine until you hit Vsat, and after that suddenly gives up, right. That's good enough for most purposes, right. So therefore the process of dynamic range scaling is necessary whenever you when you make a filter, because as we saw, there are many choices of resistors and capacitors that yield the same transfer function, right. However, they will not all be identical as far as the swings at the internal nodes are concerned, right. A wrong choice of component values can cause premature saturation of one of the op amps that are internal to the filter, and therefore that will limit the maximum input swing that you can put into the op amp. Does it make sense? All right, and this is called, as I said, dynamic range scaling, right. Now, the question nobody asked me was, why should the peak gain be 1? What if it is 0.5? All the peak gains are the same, so no one particular op amp is is messing you up. What if the peak gains are only say 0.25 or 0.1 or 0.01? Pardon? Yeah, well, one argument is that, oh well, this filter will be able to handle signals that are, if it is the peak swing is 0.1 VSAT, then in principle you can put in 10 times VSAT at the input, and the output at every op amp will then hit VSAT. He says that's that's a terrible thing to do, because well, that your supplies allow you to swing only between plus minus VSAT. So it's very likely that the input is also restricted to plus minus VSAT. Now you unnecessarily seem to have a large range, right? And the outputs of every op amp, is swinging very little, right? And it turns out that you will see why. I mean, on the face of it, it doesn't seem bad, right? I mean, what is the problem? I mean, you have a range which is much input range which is much larger than the signal level that the op amp can handle, right? What do you think might be the problem? Noise. I mean, remember, whenever you are working with signals, with circuits, if all your voltage swings everywhere are very, very small, then the output tends to be, the fidelity of the output tends to be limited by noise, right? I mean, it's like you're writing a computer program, say you're doing some numerical solution of some equations, and you find that all your numbers are changing only in the third decimal place, right? Okay. Let's say you're doing some, attempting to solve some equation numerically on a computer, and all the numbers somehow seem to be only changing in the in the third decimal place, right? Is this good or bad? Well, you know that every number has got finite precision, correct? And therefore, if all your numbers are changing only in the fourth decimal place or third decimal place, it basically means that machine precision will now have a lot more effect on round off errors, right, in the algorithm, when compared to somehow, let us say, before you got into this algorithm, you scaled all numbers so that you were using the full dynamic range of your number representation on the machine, correct? Okay. I mean, most of the time, none of you guys bother about it, because you're working with MATLAB or whatever, which has 64 bits, and that's it's very forgiving of stupidity, right? But when you're actually implementing signal processing algorithms on a chip, for instance, and where having 64 bits is simply not an option, because then your cell phone would have to be plugged into the power socket all the time, right? Where the number of bits is something that you want to keep as small as possible while still doing what you want to do with adequate fidelity. Then you want to, then you will end up facing the same issue, because round off noise in a digital system is analogous to thermal noise in analog systems, right? A resistor adds noise when you apply voltage, right? Whether you apply voltage or not, a resistor adds some noise. If you apply very small voltage, the signal power is very small, but the resistor continues to add the same amount of noise, right? And therefore, the signal to noise ratio becomes, yes. Yeah, so which is why we will discuss why we cannot have peak swings which are much smaller than 1, right? It will become, at this point it may seem harmless, but when we study noise, it will become very apparent why you do not want to work with very small internal levels, right? You do not want to work with very large internal levels, because then you stand the risk of saturation. You do not want to work with very small signal levels, because you stand the risk of getting drowned in noise, all right? you always want to work with signals which are not too large to cause saturation, not too small to get drowned in noise, right. I mean, when I am speaking to you, right, I mean, it does not help me to kind of yell at you, right, because your ear is going to saturate, right. But then if I say, oh well, oh, these guys have very sensitive ears, and if I whisper, nobody hears anything, right. Okay. So, so basically, like the Buddha said, it's always the middle path is always the best. Don't either be this extreme or that extreme, all right. And so the range of what do you call good signals to use, right, all right, which is a reasonable thing to define that would be what is the largest signal I can process without getting into saturation and nonlinear effects, what is the smallest signal that I can process without losing information because it's simply drowned in noise, right. So, every system will have a minimum possible signal you can work with and a maximum possible signal you can work with, right. This ratio of minimum possible signal to maximum possible signal is called the dynamic range, right. Today, with the what you know so far, you can you probably only appreciate that there is a maximum limit, right. When we discuss noise, we will discuss the minimum limit, right, and the ratio of the maximum limit to the minimum limit is what is called dynamic range, right. Okay.